All right, hi everyone. We'll get started. Welcome to your last little bit for your last exam. Yay. We'll just jump right into it. Just remember that tomorrow at 10:20 you'll be taking your exam. So just make sure you show up on time, bring a calculator and a writing utensil. And then 15 minutes later you'll be done. Any questions about the exam, not content related? I'll be there tomorrow, so if you have anything before the exam begins, just let me or Dr. Mock will be there as well, so you can ask him as well. Okay, so we'll just jump into it. What questions do we have? It can be a general thing or it can be something from the mock exam. I just pulled it up because we did some of that yesterday. But you can either take yourself off of mute or just answer it in the chat. Yeah, absolutely. Let me just pull up my answer key, sorry. All right, so when we look at question 5, right, question 5 reads that pyridine C5H5N is a weak base with Kb 1.7 times 10 to the negative 9. Calculate the pH of a 1.5 molar or 0.15 molar pyridine aqueous solution. So the main point here is that you are given pyridine and you're asked for a pyridine aqueous solution, which means that that is your starting material on your left-hand side of your equation or of your ice table. So you have C5H5N, and that's going to be in solution, which means that we're putting it with water. And then you were going to form an ice table because we know that C5H5N is a weak base, so it will form an equilibrium. So we'll form, right, a conjugate acid is going to be plus 1 hydrogen. So we'll have C5H5NH plus and OH minus. And then we can form an ice table. So then we'll have ice. We don't care about the hydrogen. We have a starting concentration of the pyridine of 0.150. We don't have anything for our conjugate acid or our OH. We'll have minus S plus X and plus X, because if you solve for Q, you would see that Q is equal to 0. So Q is less than K. We have to form some products. So then we have 0.150 minus X, X, and X. And then we can use the KB, because KB is your acid times your OH minus over your base. So this is X times X over 0.150. We don't have to, or we can use the approximation. We don't have to use that X. We can just say that that's negligible, and that will be equal to 1.7 times 10 to the negative 9. So KB, or I guess what this equals is that X squared, right, will equal 1.7 times 10 to the negative 9 times 0.150. So X will equal 1.6 times 10 to the negative 5. What does that give us? What does X give us, and what can we use from X?
OH.
Perfect, right? So that's a concentration of OH. So we can get the POH, which is the negative log of 1.7 times 10, oh, sorry, 1.6 times 10 to the negative 5. POH will equal 4.7967. And how do we get to pH? Does that right? Does this answer our question?
14 minus the POH.
Perfect, right? So we know that 14 minus POH will equal pH. So 14 minus 4.7967 will equal 9.20 when you round, which is A. Okay, any questions on 5? Does that make sense for how that gets done? Right, remember that yes, yep, so someone said we know that it becomes a conjugate acid in OH since a weak base will always form a conjugate acid, and that's correct, right? In order, a base is always going to be a proton acceptor, so we're going to take one of the protons away from water, leaving behind an OH and its conjugate acid, right? If we have a weak base, we have to have a conjugate acid as well. That's a great question. So someone asked, what happens if you convert KB to Ka using Kw and try to solve? So that would be encouraged if you were given a solution of the CH5H5NH plus. Kb is base equilibrium. Ka is acid equilibrium. Since when we set up our ice table or our chemical reaction, we have a base forming OH minus. Kb uses OH minus. So OH minus has to be used here, or Kb has to be used here because we're forming OH minus. If we solve for Ka, that's not going to give us the answer that we're looking for because we're not talking about the acid equilibrium or the acid dissociation. We're talking about base dissociation. So using Ka here, even though you're looking for the pH, still does not give you the H plus concentration that you're looking for. Does that make sense to my person that asked? Great. Okay. Any other questions on 5? Right, if they asked you for, instead of the pyridine, if they asked you for pyridine H plus solution, then you would want to convert to Ka. Okay, someone asked for 8. Yes, so we did do 8 last night as well. So I'll just do a brief rundown of 8, but that is broken down in last night's review session. So you can also look there if you need a better explanation or you need more explanation because I talked about that a little bit. So for this question, right, you can see a couple notes that I've already made. So for tris is a weak base widely used to make buffers for the study of biological systems, and the conjugate acid of tris can be written as tris H plus, and the Kb of tris is 1.17 times 10 to the negative 6 at 25 degrees Celsius. You want to consider a 1 liter buffer that is 0.1 molar in tris and 0.1 molar in tris H plus. Calculate the pH of the buffer after the addition of 5 mils of 10 molar HCl. So You can see that I already wrote that we have a strong acid in HCl, so we expect a lower pH than what we're at right now. So we don't know what pH we're at. We could find that if we wanted to. It's not necessary for this equation, but we are expecting to get more acidic with the addition of HCl. So slide 18 in your slides goes over something very similar to this if you need another refresher or just more practice when we're done here. But what you want to do is that you have your addition of HCl. You need to figure out how many moles of HCl you have. So you're going to take your 10.0 molar, which is moles over liter, multiply that by 0.005 liters, and then we end up with 0.05 moles of HCl. If we have 0.05 moles of HCl, that is going to break apart into H plus and Cl minus. So if we start with 0.05 moles of HCl, that means that 0.05 moles distributes to 0.05 moles of H plus and 0.05 moles of Cl minus. Do we care about the Cl minus in this case? No, someone in the chat said no. Nope, we do not care about the Cl minus, so we can just kind of ignore that. If we're adding H plus and we have tris and water forming tris H plus and OH minus, what is that H plus going to react with? What does that additional H plus react with?
Does it react with the HCl? Or no?
Nope, so the H plus came from the HCl. So we no longer have HCl in solution. Like when we add those 5 milliliters, it will like immediately dissociate into H plus and Cl minus. So now that we have additional H plus in solution, what is that going to react with?
That tris base.
Yep, that tris base is what's going to react with it, right? When we add more acid to a basic solution, or when we add more acid, it'll react with the conjugate base. If we add more base, then it will react with the conjugate acid. So this H plus and this tris will react. How much tris do we have? We can figure that out. We have 1 liter of tris, and we have 0.1 molar of it. So we have 0.100 moles of tris. So we have 0.1 of tris that's going to react with 0.05 moles of the H plus. And what does that form when tris and H plus come together?
The tris H plus.
Perfect. It forms the tris H plus. So the tris plus, and then which one do we have less of, the tris or the H plus? What is our lesser quantity? What is our limiting reagent?
The H plus.
The H plus, perfect, right? So we're going to use up all of that H plus. So we're going to subtract 0.05 moles from this. So we get 0.05 moles of tris remaining, and that forms the tris H plus. We have 0.01 moles of tris H plus, and we're going to add 0.05 moles, right? Because everything is 1 to 1 to 1. So we end up with 0.15 moles of tris H plus. How does that help us? Where do we get, what can we use from there?
we use the moles from the ice table and plug it into the buffer equation?
Yes. Yep. So you do want to use concentrations technically for your buffer solutions. However, in this case, if we were to solve for the concentrations of our tris and tris H plus here, it would be the same, right? You're dividing by the same liters and then you're dividing, so it would cancel out. But you technically want to put concentrations in the Henderson-Hasselbalch equation. So you should technically divide these by the total volume, which is 1.005. So you end up with 0.498 and 0.1493 molarity for both of these. So that's technically what you should be putting into your equation. But then we have pH is equal to pKa plus the log of base over acid. Wow. Do we have the pKa?
No, but we can find it from the KB.
Perfect, right? So we're given Kb. So we can take Kw is equal to Ka times Kb. And we'll say that 1.0 times 10 to the negative 14 divided by 1.17 times 10 to the negative 6. And we get 8.55 times 10 to the negative 9 as Ka. So we'll take negative log of 8.55 times 10 to the negative 9 plus the log. What goes on top? What value? Yep, so someone said the base tris, and that's correct. So we're going to take 0.498 over 0.1493. And we'll see that pH is equal to 7.59, which is C. Okay. Does that help for the people that needed question 8? Again, I do a little, yep, absolutely. Sorry, go ahead.
I had a question about the molarity of tris. So my 0.05 moles divided by 1.005, I'm getting 0.049.
That's probably right. I probably just copied wrong. Yep, yeah. Yep. Okay, and then if you need any further explanation on 8, or if you need a way to check your answer, we talked about that yesterday. So you can just look at that review video. I think that was towards the beginning, so you don't need to jump very far. Okay. Yep, so for 13, we also talked about this last night, so you can also have a more in-depth discussion there. But for 13, what you're looking for is that you are looking for a buffer solution. So that kind of talks into what we talked about in class yesterday. Review videos are always posted under the office hours tab. So if you could just go to the main homepage and scroll down, it's office hours, and then you just scroll down a little bit there, and it says like review videos all the way down. So for these, we're looking for things that will produce a buffer. And we know that a buffer is going to be a weak acid or base, and then it's weak conjugate acid and base. So if you see something where you have a weak acid and then a weak conjugate base, that'll automatically make a buffer. So in B, for example, we have HF, which is a weak acid, and we have NaF. NaF will dissociate into Na plus and F minus. That F minus is the weak conjugate base of HF. So automatically you know that B is going to make a buffer. For A and C, we have a weak acid and we have a strong base that's being added to it. So we don't know if that's going to work or if that's going to make a buffer. But we know for certain B will make a buffer. So on your exam, when you're looking at your answer choices, you should say, okay, I know that B will make a buffer. So what does that narrow my choices? Narrow my choices down to? Is B my answer? Maybe, but we look at D and we see both B and C is an answer choice. So that should indicate that A will not produce a buffer, because if B we know is correct, then it's either just B or it's B and C, but it cannot be A. So you should immediately be able to eliminate A as an answer choice. It will not create a buffer. The next step you need to look at is, does C create a buffer? And in C, this talks about if we're still in that buffering range, like of that titration that we started to introduce on Wednesday. So you need to see how much of your weak acid and how much of your strong base you have in your solution, and do you still have buffering capacity? Do you still have your strong acid or your weak acid and your weak conjugate base? That's what you need to be asking yourself. So if we look at, if we look at 100 mils of 1 molar HF, we see that we can solve for the number of moles of HF, and we get points. What am I saying? We have a start of 0.1 molar HF, or 0.1 moles of HF. For sodium hydroxide, we have 100 milliliters, and then we have 0.5 molar. So if we do that math and we say, okay, we have 0.5 molar and 0.1 liters, then we have 0.05 moles of sodium hydroxide. So the same thing that we just did, where we had a weak base with tris and then we added acid, we're doing the same thing here, but this time we have a weak acid of HF and we're adding strong base. So that strong base will react with HF to produce HF and F minus, right? Because if we switch partners, like we see over here, if we have HF and NaOH, this will switch partners to NaF and H2O. But we know that in solution, NaF will dissociate into Na plus and F minus. So you'll have Na plus and F minus floating around. So when we use up all of our NaOH, we no longer have that in solution. We just have water and Na plus ions and F minus ions. We're still left with a little bit of HF. We've also now produced F minus. And how much did we produce? Or how much did we produce? Is we produced 0.05 moles of F minus. So right now we have HF in water forming F minus and H3O plus, and we have 0.05 moles here and 0.05 moles here. So do we have a weak acid and its weak conjugate base present in C? Yes, we do. So that means that C will produce a buffer. We still have both of those components available to us for it to buffer. And so that will create a buffer. So D is your correct answer because both B and C will produce a buffer. Does that make sense for 13? Are there any other questions on 13? Cool. Okay. Can you do question? Chapter 19 slides. So someone asked for the question on slide 21 on the chapter 19 slides. My slide 21 that I can see is the definition of buffering range and buffering capacity. I don't know if I need to go up or down.
Hi, yeah, I asked the question.
No problem.
It's the question that says it starts a nitrous acid / sodium nitrate buffer has a pH of 3. That's the first sentence. She mentioned it yesterday in class and said it'd be good to know before the exam. So
Yes, okay. Yep, I got it. So, right, this is the question we did first, so it was a okay. And then we said that Ka is equal to. Okay, so for this question, what we're looking at is the fact that we have a nitrous acid and sodium nitrate buffer has a pH of 3. We're given, right, we want to know the concentrations of this acid and conjugate base, given the Ka and given that their concentrations equal a certain value. So what you should look at first is identifying if you have a strong acid, strong base, weak base combination. What's going on here? So for HNO2, is that going to be a strong acid or a weak acid? Or a strong base and a weak base? Good. So this is going to be a weak acid. All right. HNO3 is our strong acid. So one less oxygen makes it a weak acid. So that means that if we have a weak acid, what do we classify NO2 minus as? Good. This is its conjugate base. And is that going to be a strong or weak conjugate base? Good. This is a weak conjugate base. So, right, we have an acid, we have a weak acid and its weak conjugate base. We have a buffer solution, and we're told that we have a buffer. So that means that we have the ability to use pH is equal to pKa plus the log of base over acid. What we know from this equation is that we have a pH of 3 and we have the Ka. So we can plug in pH of 3 and the negative log of 7.2 times 10 to negative 4. But then we're left with this log of base over acid. So this is 3.00 equal to okay. So we can solve for just the log of base over acid. So we get negative 0.14267. So once we get to this point, we have to undo our log. So we have to take the base 10. And we get that 0.72 is equal to the concentration of the base divided by the concentration of the acid. So now it's saying, okay, how does this help us? So in a multiple choice type setting, right, you could sit there and you could plug in your answer choices to see if any of the combinations give you 0.72. Maybe 2 of them give you 0.72, so then you have to kind of decide what to do from there. But as a test taking strategy, if you don't know where to go from someplace, use the answer choices to your advantage. But the other thing that we know is that we have the concentration of our acid plus the concentration of our base is equal to 0.2 molar. So we don't know what the concentration of our acid is. So X could equal the concentration of HNO2. We know that X plus the concentration of NO2 minus is equal to 0.200. So we can say that the concentration of NO2 minus is equal to 0.200 minus X, right? It's whatever is made up of that 0.2 subtracted from the acid. So now, instead of having two variables, right, instead of calling it X and Y, you can now plug this in where 0.72 is equal to 0.200 minus X over X. Hey, does that make sense how we can utilize that additional information given to us in our question to our advantage? Okay, so then it just becomes solving for X again, right? Just a little bit more algebra. So we got that X is equal to 0.116. And what does X correspond to?
HNO2.
Good, that corresponds to HNO2. So concentration of HNO2 equals 0.116. So on your answer choices, the only two answer choices that have HNO2 equal to 0.116 is C. So, right, that should be a good indicator that that is a correct answer. But in order to check to make sure that NO2 minus is proper, you could say that 0.2 minus 0.116 is 0.0884. Yeah, 0.084 molar, and that would check out. Okay, does that help my person that asked that question?
Yes, thank you.
Yep, absolutely. Okay. Okay, someone asked for 15 and 16. I think I did that very quickly at the end of yesterday. I think 6 we did yesterday. Yeah, 6 we did yesterday. I know that was towards the beginning as well. Someone asked for 11. Yeah, 11 we did. Or no, wait, 11. Yes, 11. 11 I can briefly do. So when we go down a periodic table, if it's just HF, HCl, HBr, HI, as we go down, acidity increases. So, right, when it's just the H plus and whatever halogen it's with, or even if it's H plus and a different group going down, acidity will always increase. This is because the size of your molecule is increasing. And as the size of your molecule increases, you have more electrons in that atom. So if you give that atom an additional negative charge, right, if it becomes Br minus, if it becomes I minus, it is now bigger and has a better time distributing that negative charge and taking on that negative charge. And so it's a little bit more stable as a negative. Therefore, it's okay with getting rid of that H plus ion because it can stabilize itself on its own. Right, and if you think about it in terms of, okay, HF we know is a weak acid, but HCl we know is a strong acid. So as you go down the periodic table, we increase in our acidity a lot, right? Enough to make it a strong acid from a weak acid. So going down a periodic table, when it's just hydrogen and an atom, acidity increases. When you start adding oxygen in there, then that changes. Then the trend reverses. So the smaller the atom with an oxygen will now have greater acidity. Again, having to do with the electrons. So if there's an oxygen in your system or in your molecule, then you want to say, okay, as I go up the periodic table, as size decreases, then my acidity increases. Okay, so that's why we can narrow down to H2CE, because H2S and H2SE are, right, are just, it goes S and then SE. So as we go down the periodic table, Se will be more acidic than sulfur. So that narrows us down to HClO2 and HBrO2. And now when we look at chlorine compared to bromine, chlorine is smaller with the oxygen. So then we will increase our acidity with the smaller atom when it becomes to oxo acids. So HClO2 will be your stronger acid there. That also makes sense because we have something HClO4, but we don't have an HBrO4, right? We don't have one of those because that's considered a weak acid. The smaller the atom, the better it is at being an acid in this case. And then what we talked about yesterday as well is that if you're increasing the oxygens, HClO2 compared to HClO3 compared to HClO4 is increasing in acidity. So the more oxygens you have, the more acidic that atom is, or that molecule is. Okay. Is any other questions on 11? Does that help with 11? To briefly look at 15, and then someone also asked how to identify the difference between a Lewis base and a Bronsted-Lowry base. So to look at 15, right, we're asked for the Lewis base in this atom, or in this reaction. This is something that you, like if you're in the group meet, it asks for complex ions, like this is what you're gonna have to be identifying in terms of complex ions. So when you draw out the structure, you see that bromine only makes 3 bonds. It's stable as 3 bonds and has no lone pair. Oxygen has 2 lone pairs, and it has the methyl groups hanging off at the side. A Lewis base is a lone pair donor. So those lone pairs can donate to bromine in order to form the complex ion. For a Bronsted-Lowry base, we know that this is a proton acceptor, right? So if a Lewis base is an electron pair donor or a lone pair donor, it is the inverse, I guess I'm going to call it, for the Bronsted-Lowry. Instead of talking about electrons, we're talking about protons. Instead of being a donor, it is now an acceptor. So when we talk about Bronsted-Lowry, it's all about the H+, right? What's happening to the H+, where is that going? When we're talking about Lewis, this is all about the electron. Where are the electrons going? How is that distributing, and what's happening that way? So someone asked, yep, anytime. Someone ask, do you have any recommendation on how to draw structures or go about answering questions like 15? So my biggest piece of advice is to try and remember Lewis structures as much as possible, or to think about it in the most simplest form as possible, right? We know water. I think we could all draw water. We know that it looks like this, right? It has 2 bonds and it has 2 lone pairs. When we think about water, we then have to look at OCH3 2, right? That's doing the same thing as if I wrote water as OH2. It's just putting a more complex thing attached to the oxygen. So you're going to draw it the same way. It's just going to look a little different because something, or not hydrogens, are hanging off of the oxygen. Now carbons are hanging off of the oxygen. So if you can remember that or try and break it down into the smallest version, that might be able to help. And then just like the basic, most things. So someone asked, wouldn't BCl3 have 28 electrons? It only has 24 electrons. Your electrons come from your periodic table. So boron is in your 3rd row, right? If you look at, or it's technically 13, so you subtract 10 from that. So this only has 3 electrons, and chlorine is in group 17, so minus 10. So this has 7 electrons. So you have 3 plus 7 times 3, so 24 total. You used 6 from your bonds, so you have 18 left over, and that goes to the lone pairs on chlorine. So there are no electrons on boron. Boron is very stable with 3 bonds only. So most of the time, boron will only make 3 bonds. Yep, so then the boron accepts a lone pair as the Lewis acid from the oxygen forming this compound. So then we get BO CH3, CH3, Cl, 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 something like that. Right, so this is your Lewis acid. This is your Lewis base. For 16, right, 16, we did at the very end yesterday, but it's asked for delta G. So we do know that delta G is equal to delta G naught plus RT ln of Q. So you need to solve for Q, and you also need to solve for delta G naught. Delta G naught is equal to negative RT ln of K. So it's using the same concept as question 1, but this time you're just using your values that are given to you from a graph. So that's for 16. For di and triprotic acids, if you have something like H3PO4, you have to write each acid dissociation as only 1 proton being removed at a time. So when H3PO4 is in solution, this will form H2PO4 plus minus plus H3O plus. This is now another acid, and H2PO4 minus can form H plus H2O can form HPO4 2 minus and H3O plus. We have one more acid, and that can be HPO4 2 minus plus water forms PO4 3 minus and H3O plus. Your first equation, the first atom or the first proton that gets removed, this is Ka1. The second atom is Ka2, or the second proton, and the third one is Ka3. So someone asked which Ka do we use? That's very dependent on the question. So in question 10, you have a solution of Na2HPO4. Since NH2HPO4 is going to split up into Na plus or 2 Na plus and HPO4 2 minus, you're forming PO4 3 minus. This is the third equation in the dissociation of phosphoric acid. So we have to use Ka3 for this one because that's the acid that's going to be in solution that's going to be forming the Ka, or that's going to be forming the acid dissociation. If this solution was NaH2PO4, then that would be Ka2 instead of Ka3. Awesome. Okay. And then someone asked, why KClO4 in this example doesn't have a Ka of 1 times 10 to the negative 7 since it's neutral. I have not had time to figure that out. My apologies. I don't know, but I do know that it doesn't. What my brain is telling me is that because we're looking all at acid dissociations, we would have to look at what happens when KClO4, right, isn't, or as KClO4 is in solution, right? So if this accepts the proton, we then have HClO4, which shoves it back towards the shoves it back for just the HClO4, meaning that we're looking at the inverse of a very large Ka, which is going to be very, very small. Is that totally what's going on here? I think there's something else. I just haven't been able to fully form an answer for that one, so I apologize. Think it's just a little bit more complicated saying that it's neutral, because other stuff is happening. So I apologize. I have not seen the exam, so I don't know if a type of question like this is on it. But she might just trying to get you to think about which Ka is the most acidic. So maybe she'll give you a slightly easier or more straightforward question on the exam. Is my hope for all your sakes as well. Okay, and then I think I tried to answer it with everything else being answered as well, but right, do you have any general recommendations for exams? The biggest thing that I can give you, or biggest piece of advice I can give you, is to use your exam to your advantage. You have multiple choice questions, so most of the time you know enough to get to an X value of some sort, right? You know you need to solve for X. Plug those answer choices that you have into that X component and see if you can get something of resemblance that sounds like a correct answer. Use your test to your advantage, as in question 1 on the mock exam asks for delta G. And then you then have to then solve delta G later on in the exam as well in question 16. These two things are the exact same question. You're just pulling your data from different areas. You're pulling your data from the question in question 1. You're pulling the data from a graph in question 16. So same concept is being asked. It's just being asked in 2 different forms. So if you could solve question 1, you can solve question 16. What other tips do I have? If you have something where you're saying, what is the most acidic? It will be an extreme, right? Or the most or least acidic, it'll be an extreme. So if you change all of everything in question 2 to pH, say, anything in the middle will not be the answer choice, right? You might be a little confused and be like, wait, what are they really asking for? But whatever's in the middle is not the answer, because most or least are like definites and they are extremes, and they're either going to be the highest or the lowest answer. But if you can knock 2 of them away, that gives you a better chance of picking the correct answer. What else? You're going to see a lot of acids and a lot of bases on this exam. use that to your advantage. If you look at something that says CH2H5CO2H, right, as a chemical compound, and you're looking for the conjugate base, right? Always come back and reference this if you're trying to say, okay, if this is a conjugate acid, like what does that mean? Blah, blah, blah. Look at the difference between your acid and your base in your question. Or even in 8, right? You have a weak base of tris. You then have the conjugate acid of tris H plus. In your question, it's telling you this is the base, this is the weak base, and the conjugate acid is just tris with an extra H plus. So if you're looking for the difference between them, the only difference is that the acid now has an extra H plus. So that you can always refer back to that and say, what's the difference here? How does that compare to the question I'm answering now? It can only ask you so many buffer questions. So same equations and same types of things will pop up multiple times in one exam. Use that to your advantage. And then always make sure you're using your formula sheet to your advantage as well, right? It's given to you. If you don't know what to do, look at your formula sheet to see if something jumps out on the page, right? If you're solving for pH, maybe look for an equation that has pH. If you see the word buffer, be like, okay, I probably have to use the Henderson-Hasselbalch at some point, right? How can I get to something that I can fill that equation in with, and use that to your advantage as well. And at the end of the day, just make sure you answer every question. Because it at least gives you a 25% chance of getting it right. Does that help us there a little bit? Of course. I say that as someone that's taken many exams, so it might sound a little straightforward from me, but y'all are at the start of your careers for most of you, so you have time to learn how to take a test, and this is just part of the learning curve. And I promise you'll be better test takers if you can use it to your advantage. And at the end of the day, take a deep breath. It's going to be okay. You will be okay. It's just one test. And then you have a final, and then you're done. And because you're being tested on this, the final will not cover this as much as all the other content that you will learn. So, yay. Okay, are there any other questions for me? Y'all are gonna do great.
Could you just do like a really brief kind of summary over like Q and K and just all of that we
Yep.
need to know?
Yep. So Q is questioning, right? You don't know where you are, and so you are questioning where you're at. It is set up the same way as K. And it can be and Q is for non-standard conditions. Or not equilibrium. It could be equilibrium, but that's a specific case when Q is equal to K. In terms of KSP, this is your solubility product. So when Q is less than KSP, your salt is more soluble, as in more ions form. And when Q is greater than KSP, salt is, I guess, salt is formed, right? Precipitate forms. As in, this is not enough ions. And this one is too many ions. Looking at the formula sheet, right, Q is here for non-standard conditions, and K is here for standard conditions. Okay, so equilibrium is at standard. Non-equilibrium is non-standard. A large Ka is equal to a low pKa, which is equal to a low pH. This is very important here, where Kw is equal to 1.0 times 10 to the negative 14 at 25 degrees Celsius.
My answers seem to like differ whenever I use 1.01 times 10 to the negative 14. So would you recommend just like kind of following what the sig figs of the Ka are, or to always do 1.0?
I think if you get 1.0, you'll be close enough. You could also check it briefly if you have time, right? You have a multiple choice question that should be close enough if you use 1.0 or 1.01 that you should still get the correct answer. It might be off by 1 or 2 decimal points, but that is close enough to still choose that for the
Okay, thanks.
question. Yeah. Though someone asked in 16 why we use delta G standard. So for delta G standard, this is or where is this? For delta G standard, we have to use K, and K is equilibrium. So where they intersect is not equilibrium. Equilibrium is where concentration no longer changes, and so that's about the 5-minute time point. So we need to use the values at equilibrium for delta G naught, but then for delta G at 2.3 where they intersect, then it's going to be the 0.0035. I think that's the big things on K and Q. That's really KSP and like delta G stuff is where you see that the most for this exam. Okay. Any other questions? Gonna be okay, I promise. And it's Friday tomorrow, so you take a test and then maybe you have one more, but it's Friday and then you have the weekend. And if you're going to Chili Fest, have fun. Okay, I think we'll call it good for today. Make sure you sleep. One of my test taking strategies, make sure you sleep. Make sure you listen to some calm, relaxing music before you come to class. Make sure you eat breakfast, fuel your brain, and then you can review a little bit in the morning. But what you know tonight is if you sleep and let your brain recover, then you will be able to do well tomorrow. You can remind yourself of the important things, but don't try to teach yourself anything new right before the exam because then you'll forget the stuff that you already know. Be confident with what you know. You know more than you think. Take a deep breath and at least just start a question. If you don't know how to do it, come back. I always tell my students that when I took my AP exam in high school, I got to the free response and I did not answer a single free response question in its entirety this first time I looked at it. I answered question A and I moved on to part 2, right? Or I moved on to question 2 and did A, B, C, didn't know how to do D, and I came back to it, right? It's okay to start a question and come back. Okay, thanks everyone. Once I get the recording back, I will post it. If you need to look at that again, you can listen to it like a podcast, and we'll call it good. Good luck. I'll see you tomorrow morning. Sleep tight. You're very welcome. Happy to do this. Good night, y'all, and good luck.